In this lesson, we're going to look at integrals of vector motion. Let's start with the function r of t, which is differentiable and continuous across its interval. If we integrate r of t with respect to t, we get its antiderivative, big R of t, plus a constant. Let's move that up. And what we want to remember here is that when you integrate a function, there are an infinite number of functions that satisfy the antiderivative. Here's the antiderivative plus a constant. So there's an infinite number of constants that can be added to the antiderivative such that the right-hand side of this equality becomes differentiable, giving us the integrand here. Here we're going to start with the function r of t, and we're going to integrate it. So it's the cosine of t in the I direction plus 1 times the j direction minus 2t in the k direction. So move this up, and what we want to do is we want to integrate r of t. So that means we're going to integrate, we'll put this in brackets, the cosine of t in the I direction, this is our r function, plus 1 times the j direction minus 2t in the k direction, all integrated with respect to t. Okay, so I'm going to change the 2, the minus 2 to plus a negative 2, add the opposite. And now what we're going to do is we're going to integrate each term. First we'll integrate the cosine of t, and the antiderivative of the cosine of t is the sine of t. So it's the sine of t, and this is plus some constant, we'll call it constant 1, and this is in the I direction, plus the antiderivative of 1 in the j direction, and the antiderivative of 1 with respect to t is dt, is t, plus another constant, and that's in the j direction, plus the antiderivative of a negative 2t is a negative t squared plus a constant. We'll call that c3, and that is in the k direction. And let's take this and we'll move this right up underneath. So this becomes the sine of t in the I direction plus a constant c1 in the I direction plus t in the j direction plus a constant c2 in the j direction plus a negative t squared in the k direction plus c3 in the k direction. And we'll move that up. And what we want to do is we can actually commute, because this is all addition, where we have we can put our sine of t and our t squared together, and our constants, the c1, c2, and c3 terms can be put together. So let's do that. So we have the sine of t in the I direction plus t in the j direction plus a negative t squared in the k direction, And here I'm going to put the constants in parentheses. We have a c1 in the I direction plus c2 in the j direction plus c3 in the k direction. And let's move that up. And what we end up with is that we put our constants together as one constant, okay? And we end up with the sine of t in the I direction plus t in the j direction plus a negative t squared in the k direction plus a constant. And so what we have here is the antiderivative of r of t. Now we just found the antiderivative of the cosine of ti plus j minus 2t in the k direction. Now we're going to find that antiderivative with our bounds 0 to pi. So we are going to take our antiderivative and figure out what is it from 0 to pi. So we're going to start with pi and take the sine when t equals pi in the I direction plus t equals pi in the j direction, minus pi squared in the k direction. And this is there's our antiderivative when t equals pi, minus, and this is the fundamental theorem of calculus, part 2. Here we're going to take the sine of 0 in the I direction, plus 0 in the j direction, minus 0 squared in the k direction. We want to solve this, so let's move this up. And the sine of pi is 0, so we have 0 in the I direction, plus pi in the j direction, minus pi squared in the k direction, and I'm going to put that in parentheses, minus the sine of 0, again is 0, so we have 0 in the I direction and 0 in the j direction, minus 0 squared in the k direction. So actually we lose this piece. Okay, so let's move this up. And so our final answer here becomes pi in the j direction minus pi squared in the k direction. And this gives us the antiderivative of r given the bounds from 0 to pi. Imagine that we know the acceleration vector of a moving object, but not its path. And we know the object's initial position. We want to find the object's position as a function of time. Here we have the acceleration function with respect to time. We have negative 3 cosine t in the I direction, minus 3 sine t in the j direction, plus 2 in the k direction. At t equals 0, we are at a position, or the particle starts at a position of 4 units in the I direction and no units at the origin in the j and k direction. And the velocity at time 0, which is the initial velocity, is 3 units in the j direction. Let's work out this problem. Now, looking at our acceleration, we know that the acceleration is the change in velocity with respect to time. So dv dt is equal to our acceleration. Let's move that up. So we can write that as dv is equal to the acceleration times dt, and what we want to do is integrate both sides to find the velocity. So let's do that. We're going to integrate the negative 3 times the cosine of t in the I direction minus 3 times the sine of t in the j direction plus 2 in the k direction, and this will be integrated with respect to time. And the antiderivative of the cosine is the sine, so we get a negative 3 sine of t minus 3, and the derivative of the sine is the negative cosine, so there's making that positive cosine t in the j direction, plus 2t in the k direction, plus our constant. Let's move that up. Now, what we do know here is we have an initial condition. At time is 0, our velocity is equal to 3j. So what we want to do here is we want to say the velocity at time 0 is equal to 3j, which means that 3j is equal to, let's move this up, what we're going to do is we're going to take our velocity equation right here and replace our t's with a time of 0. And that gives us a negative 3 times the sine of 0 in the I direction, and it looks like I forgot an I right there, plus 3 times the cosine of 0 in the j direction, plus 2t, t is 0, in the k direction, plus c. And again, we're trying to find c. So we get 3j is equal to, well, right here, the sine of 0 is 0, so we lose this term. We also lose this term because 2 times 0 is 0, but we keep this middle term here because the cosine of 0 is 1. So we get 3 times 1, or 3j, plus c. And clearly from this we can see that c is equal to 0 in order to have this inequality work. So what we get here is that our velocity equation from this, our velocity with respect to time equation, is equal to a negative 3 sine t in the I direction plus 3 cosine t in the j direction plus 2k, or 2t in the k direction. There we go. This is our equation for our velocity, our constant, because we know our constant is 0. Now we also know that the velocity is equal to dr dt. So the change in r with respect to t gives us our velocity. So what we want to do is, if we actually want to find our position equation, we know that r is equal to the antiderivative of dr, which is the antiderivative of the velocity with respect to t. And let's take this and let's move this up here to give ourselves some room to work. And I'm going to start working underneath. And we are going to take the integral of our velocity equation, which is a negative 3 times the sine of t in the I direction, plus 3 cosine of t in the j direction, plus a 2t in the k direction, and this will all be integrated with respect to t. And when we do this, we find that r is equal to the derivative of the sine is a negative cosine, so this becomes positive 3 cosine of t in the I direction, plus the derivative of the cosine is the sine, so 3 times the sine of t in the j direction, plus the antiderivative of 2t is t squared in the k direction, plus a constant. Now, we know that our initial position is this point right here, 4, 0, 0. So that means that the initial position when time is 0, r sub 0, is equal to 4 in the I direction plus 0 in the j direction plus 0 in the k direction. And as we did with our velocity equation, we want to find out what is the value of c. So we're going to set this equal to a 3 cosine 0 in the I direction. We're putting a 0 in for t, plus 3 times the sine of 0, plus a 0 squared in the k direction, plus c. And what do we get? The cosine of 0 is 1, so we get 3. Oops, let me erase that there. 3, just a 3, because 3 times cosine of 0 is 1, so 3 in the I direction. Plus, we can see that we have nothing in our j direction, missing that j, and we have nothing in the k direction, but we do have a c. So we say 3i plus c, and on the left-hand side we have just a 4i. So now we know from this that c is equal to I. This just allows us to give us our equation for our position, r of t, is equal to, and what we do is we go back to our r of t equation right here, but we have our constant now, which is I. So we end up with a 1 plus 3 cosine t in the I direction, plus 3 times the sine of t in the j direction, plus a t squared in the k direction. And what you can see here is that c is equal to this I down here. And I put that in over here by putting, let's get a different pointer here. Let me get a pointer that's a little bit smaller. Let's see, I'll use a little dot here. Okay, so you can see me, I'm circling this 1. See the 1 right here? That is 1 times I. So it's 1 in the I direction, which is what we've got right here. So this right here gives us the equation for our position vector.